Good morning, everyone. I'm Enrico Manfredi from Politecnico di Torino, master student in electronic engineering. And today I'm going to present you my work that revolves around comparison between tightly coupled accelerators developed by means of instruction set extensions and loosely coupled accelerators for what concerns data compression in space applications. The development of the accelerators has been done using ASIP Designer, a tool by Synopsys that allows to use processor models to develop this kind of accelerators. They have been simulated and then synthesized to compare performance and area results, and then they have been integrated inside the Noel 5 processor from the grlib library. The code, the algorithm used for this work is the CCS-DS121 algorithm, which is a standard algorithm for data compression that features two main computational steps. The first one being the preprocessing step, where a reversible function is applied to each input sample, and then each block is compressed by choosing the techniques that gives the best compression size among a series, several techniques. The reference code implementation used for this work has been taken from the OBP Mark GitHub repository, where an open source repository where a bunch of computational benchmarks for space application can be found. After profiling the algorithm using ASIP Designer, we highlighted the three main computational bottlenecks. The first one being the compressed data that are stored 1 bit at a time in the memory. Then there is the compression of a block of input samples that is iterated for every compression technique and for obviously every input sample block. And then there is the data compression, the data preprocessing, sorry, that if active is applied on every input sample. The first accelerator that I will discuss is the so-called rightward accelerator that enhances the storing of compressed data. Here samples are masked and left shifted to align them with the content of an internal register called the IncW register that holds the incomplete words of data that must be stored inside the memory. The resulting 64-bit buffer is then stored for the upper half of the buffer is stored, and depending on the total number of valid bits inside the buffer, the IncW register is updated. If this number is higher than 32, that means that the first half of the buffer contains a full word that is written inside the memory, and the lower half of the buffer contains an incomplete word that is then stored inside this IncW register. The other two accelerators are the one for preprocessing input samples. That is a straightforward implementation taken from the standard, and it features a unit delay predictor and a prediction error mapper and allows to preprocess one sample every clock cycle. And the J-block accelerators is a couple of accelerators that we can see here on the bottom that enhances the compression size calculation and the H-sample calculations. These two accelerators here have also been realized in the second version where twice the number of samples are computed with each instructions. We can now see some results for this first round of accelerators. We can see that there is a column named rewriting C because the actual code implementation has been slightly rewritten to reduce the impact of standard library function like calloc mainly, and to highlight better the result obtained by the accelerators. We can see that after adding all three accelerators, we obtain a 85% speed up in clock cycles, or 73% with respect to the rewritten code. And as we can see, the maximum frequency has not been modified by adding these accelerators, allowing the design to be synthesized at the maximum frequency, which is the same of the reference implementation. For what concerns area, these accelerators incremented the area by 9.4% with respect to the total core area. And comparing this result with the B version of the accelerator, the one that computes 2 samples with digit extraction, we can see that we have a slightly higher performance increment, but also the total area is also a little bit higher. The throughput over area ratio here is used to compare these two results, and we can see that by this metric, the B version is slightly more advantageous if the actual higher area investment is allowed. For what concerns the loosely coupled accelerators, we have two HB interfaces, a master interface to read data directly from the data memory, and a slave interface that is used by the processor to write the algorithm parameters inside the accelerators. This is the optional preprocessing step, and then data is used to simultaneously calculate all the sizes for all the compression techniques simultaneously. And after an entire block has been analyzed, the best compression technique can be found in a single clock cycles. The samples stored inside two internal FIFOs are then compressed and written inside the data memory using a second port to allow concurrent read and write operations. We can see here that for this implementation, the speedup factor is 480 with respect to the reference implementation, but this comes at a cost of a higher area investment of 47.5% with respect to the total core area. After that, the accelerators have been also integrated inside the NoL5 model from the library, both to check their correctness also outside the ASIP designer model and to compare the challenges that comes into integrating this different kind of accelerator into existing designs. The tightly coupled accelerator have been integrated inside the pipeline, modifying both the NoL5 core and the NoL5 toolchain to use the new custom instructions. And the loosely coupled accelerator have been attached to the AHB bus that is already present inside the NoL5 subsystem. The default memory has been updated to adding the second memory port. We can finally compare these two accelerator approaches, and we can see that the tightly coupled accelerator gives a good performance increment while retaining a small area increment with respect to the loosely coupled accelerators that require a high area investment, but also, in this case, achieves the best performance increments. For what concerns the integration of accelerators, tightly coupled accelerators are much harder to integrate, requiring toolchain and core modification, while loosely coupled accelerators are much easier to integrate thanks to the standard interface. And for what concerns flexibility, tightly coupled accelerators are not flexible by themselves because they are usually single function unit, but since they are operated by software, algorithm changes can be handled by software changes, while on the other end, for loosely coupled accelerators, they must be redesigned when the algorithm is changed. Also, on the actual technology implementation of the accelerators, ASIC technology is best suited for tightly coupled accelerators, while due to the flexibility reason of before, the loosely coupled accelerators are better if implemented using FPGA technologies. We can finally compare the results obtained with other work found in the literature, especially for the loosely coupled accelerator. We can see that the proposed work is comparable with other works, even though more efficient or complex solution achieves higher throughput. And for what concerns the tightly coupled accelerators, at the time of writing, I didn't find any other work for comparison, but just yesterday I found a suitable work for comparison in one of the papers in the adjacent room. And that's all I want to say, and thank you for your attention.